In today's world, Wi-Fi has become synonymous with the internet, but it only provides a means to access existing internet connections. What if Wi-Fi could be used to create more of these connections, to provide internet where there was none before? Today, we'll be talking about WiFoO, or Wi-Fi over Optical, the result of our investigation into whether off-the-shelf Wi-Fi hardware could be used to create a resilient, high-speed, free-space optical system. First, a little background. The provision of fast, reliable, and low-cost internet access is crucial for bridging the digital divide. However, that's easier said than done. Fiber optic systems are fast and reliable, but require costly infrastructure rollouts, making them infeasible for many rural areas. Traditional wireless systems can be cheaper to deploy, but suffer from lower speeds, congestion, and interference. That's where free-space optical comes in. It provides the high speeds of its fiber-based counterparts with the low infrastructure cost of wireless systems. Further, since RF loses power as it spreads, its performance at range is limited. Optical, on the other hand, is much more directed and has no such issues, making it ideal for the connection of far-flung rural communities. But why Wi-Fi? Well, it just works. We believe that the features which allow Wi-Fi to be so ubiquitous today would also benefit an optical link. This includes resilience. Wi-Fi has built-in forward error correction, which minimizes errors, even on lossy channels. It also allows for efficient retransmission of failed packets at the MAC level, once again reducing overall error. There's also the added benefit of rate control, which allows the system to adapt to changes in the RF environment by trading off performance for reliability. Then there's the modulation. Wi-Fi hardware can make use of many different modulation schemes, all the way from BPSK to high-level QAM. This improves spectral efficiency, which is furthered by its use of OFDM, which helps to reduce errors on imperfect channels. Building custom hardware which does all that would be prohibitively expensive, but all of these features are available on mass-produced Wi-Fi hardware available at extremely low costs. If we can harness these features on an optical system, we have a recipe for low-cost, resilient FSO. And all we need is to go from this to this.
Wi-Fi is technically known as the IEEE 802.11 group of standards. The specific Wi-Fi standard focused on in this investigation is the 2.4 GHz 802.11n standard with one spatial stream. A key feature of this standard is that it includes various modulation schemes and uses convolutional coding to achieve forward error correction. For this specific Wi-Fi configuration, there are 8 modulation coding schemes, or MCSs. The higher order modulation coding schemes allow for higher data rates by increasing the number of bits represented by a symbol, as well as using less redundancy. This does of course come at a cost of less resilience to noise.
RF to optical conversion was achieved using subcarrier intensity modulation and impedance matched converters in place of antennas. Wi-Fi N makes use of 20 or 40 MHz channels centered in the 2.4 GHz range. However, optical modulation works best at frequencies under 1 GHz. To overcome that, we used a mixer to down-convert this Wi-Fi signal to one centered in the 100 MHz range. The output of this mixer was then fed to the output antenna port of the hardware. A matched 50-ohm laser driver circuit was designed and connected to this output. This allows for the amplitude of the new 100 MHz signal to be modulated onto the intensity of the laser beam. The time domain view of the beam intensity now mirrors the time domain view of the mixed RF signal. On the receiving end, the process is reversed, and a photodiode converts the optical intensity back into RF amplitude, which is upconverted back to 2.4 GHz and passed to the Wi-Fi chip. This allowed us to achieve RF to optical conversion cheaply using off-the-shelf components.
A low-cost red laser pointer was selected to make the conversion to optical. However, its characteristics had to be measured as they weren't included in the datasheet. The measured characteristics show that at a certain current threshold, the electrical and optical characteristics become linear. At this threshold, the laser diode has an approximate resistance of 12 ohms, and the optical power emitted from the laser is proportional to the current through it. For intensity modulation, an offset is required for the AC Wi-Fi signal, as the laser diode only emits light for positive input current. However, the minimum offset or bias current required to produce an undistorted signal is greater than 12 milliamps. as shown. A low-cost PIN photodiode was also used, but to convert an optical signal into an electrical one. The frequency response of the laser to photodiode system was measured. It is seen that for megahertz frequencies, the input signal is greatly attenuated. However, it is still sufficient for Wi-Fi, as Wi-Fi receivers typically have a sensitivity in the order of -80 dBm. The frequency response truly shows the necessity of downconverting the Wi-Fi signal from the 2.4 GHz to the hundreds of megahertz range. It must be mentioned, though, that a reverse bias of the photodiode is necessary to receive signals in the megahertz range.
Our actual setup comprised of 2 of these Albatross boards by Riot Networks, which we placed in a custom 3D printed case. These boards were designed for use in TV whitespace applications and contain both a Qualcomm Atheros Wi-Fi system on chip, as well as a programmable mixer intended for conversion to the TV whitespace range. SMA breakouts were installed to allow connection to other analog components. The boards run a router-focused Linux distribution called OpenWRT, which implements the Wi-Fi standard using the open-source Ath9k driver. As such, it is possible to write custom software for the OpenWRT system, as well as modify the driver if needed.
Now, onto the experimental configuration. To simplify the characterization of the link, only a single direction of the channel is optically linked, whilst the other direction is connected over an attenuated coaxial cable. The transmitted Wi-Fi signal is fed into a bias T, which provides the required current bias for linear operation. It is then fed to the 50 ohms matched laser diode. Lenses are used in the optical portion of the link to ensure maximum transfer of optical signal. The photodiode receives the subcarrier intensity modulated signal. Then lastly, a DC block removes the DC signal component, resulting in an AC electrical signal that is fed into the TV whitespace board. This setup allows for the transmitted signal to be attenuated in 0.5 dB steps, up to 60 dBs. This allows for optical propagation and scattering losses to be simulated. Setting the physical distance as well as adding deliberate disturbances to the optical channel also allows for parameters to be controlled.
Our lab setup was used to investigate the performance of our system in a controlled environment without any external atmospheric effects. This involved the placement of our transmitter and receiver a fixed distance apart on custom mounting plates. We then took to testing the link in real-world conditions by pointing it out of the lab. A mirror placed on a neighboring building reflected the beam back, creating an overall link length of 260 meters. Over this distance, the atmospheric effects on the beam became much more noticeable, both in the test setup and in the performance of our experimental runs. In order to quantify performance, we required data. Wi-Fi is very complex and its design poses significant challenges to obtaining accurate but error rate measurements. Instead, we shifted our focus to entire frames. Initially, we attempted to extract the frame error rate from debug information provided by the driver, but this proved too slow. Instead, we made use of an open-source network testing utility called iPerf. iPerf works by sending a known and indexed data stream across a link and measuring the indices of packets received to determine throughput and error rates. It was modified to provide a detailed account of all packets both sent and received, allowing us to obtain meaningful data on the error rate of the link at a packet-level resolution. Another piece of software was written to run on the router boards themselves and log the RSSI and noise level reported by the Atheros chip, giving us room for further investigation.
But how does it all perform? In the subsequent slides, we will discuss the results gathered from the laboratory setup, results gathered through the real atmospheric conditions, and lastly, based on the results, we will analyze the effect that the Wi-Fi retry functionality has on the link. The default operation of Wi-Fi includes a rate control algorithm which samples and analyzes the packet error rate and then attempts to select an optimal MCS. The graph shown depicts the data rate achieved at different enforced signal-to-noise ratios, or SNRs. The rate control algorithm does appear to work on the Wi-Fi over optical link. This is evident by considering the fixed MCS3 case, shown by the blue dotted line. For higher SNRs, the higher order MCSs do indeed allow for higher data rates, and for low SNRs, the lower order MCSs enable a link to exist despite there being more noise than signal. This heat map shows that the rate control algorithm samples different MCSs despite the SNR being fixed. On the y-axis are the modulation schemes, ordered by data rate. Here there is a trade-off. If the rate control algorithm selects a too high MCS, there is a chance that the link ceases to exist, and if the algorithm chooses a too low MCS, it affects the average throughput of the link. Hence, a modification of the rate control algorithm to better suit the distribution of SNR for an optical link may help to improve data rates. The long-term SNR of the link exposed to 260 meters of atmosphere was recorded as shown. It is seen that the SNR does fluctuate through the course of the day, which means that atmospheric turbulence or scintillation does impact the link. Once again, it is shown that a logarithmic change in the signal-to-noise ratio causes a proportional change in data rate, as one would expect to see in a Wi-Fi link. The distributions of the SNR in laboratory and atmospheric environments is shown. These distributions show that the atmospheric conditions do not only attenuate the link signal, but this attenuation varies significantly, justifying the need for resilient modulation schemes.
Wi-Fi generally requires acknowledgement of received packets. When this acknowledgement is not received, the transmission will be assumed unsuccessful and the packet retried. This is done at the MAC layer, allowing it to be significantly more efficient than TCP-based retries, while also being transparent to client devices. We performed a test with this feature disabled on a link with a theoretical maximum of 60 megabits per second and a target of 50 megabits per second. As you can see, without retries, it struggles to reach that. With retries on, however, performance was significantly improved, with throughput regularly reaching the target with only minor dips. One further test was performed with a target data rate of 20 megabits per second. When the link is not running near its maximum capacity, retries become even more effective, with basically no loss occurring. This shows us that retries allow for the maximization of available link capacity and a corresponding decrease in error rates. We verified this further by plotting the error-free runs distribution of these tests. Error-free runs are the number of consecutive packets received without error. The longer these runs are, the lower the link error rate, and the longer the interval between errors. With retries disabled, we see a standard error distribution for a lossy channel, with short runs corresponding to a high frequency of errors. With retries enabled, performance significantly improves. The length of runs increases across the board.
The physical implementation must be evaluated to understand potential problems introduced by the current design. Let us consider the link budget of the 260 meter link. The conversion from optical to electrical amplifies the signal, but this is offset by the losses in optics such as mirrors and lenses. The free space channel introduces little attenuation due to scattering and propagation. However, turbulence does add various amounts of signal degradation. Interestingly, the noise floor increases. This is possibly due to high-frequency noise from the sunlight. Misalignment and optical divergence caused by manual inaccuracies and thermal expansion of buildings has been estimated from observations to attenuate by 12 dBs. And lastly, the greatest source of signal attenuation is the conversion from optical to electrical. Some possible changes that may improve the link margin include adding a low-pass filter to reduce high-frequency alias noise from the sun and using longer wavelength infrared lights. Infrared light experiences less atmospheric attenuation, and the photodiode is more sensitive to infrared.
While the investigation results are promising, there is still significant room for improvement, which could push such a system to commercial viability. The new Wi-Fi 6 or 802.11ax standard improves performance by increasing the maximum channel bandwidth to 160 MHz, 4 times that of Wi-Fi N, as well as providing more efficient modulation schemes. Since optical systems are not bandwidth limited, benefiting from this performance improvement should be trivial and allow for speeds in excess of 1 gigabit per second. Our current setup only makes use of one spatial stream, or antenna. Most modern Wi-Fi hardware supports multiple input, multiple output, using multiple antennas. This could be used to create multiple optical streams and multiply performance. Further, the Ath9K driver is also entirely open source and controls large parts of the system's Wi-Fi implementation. This could be modified to improve performance in an optical context.
Thank you. We hope you enjoyed our presentation.